Today we're going to look at rationalizing denominators and rationalizing numerators. So rationalizing the denominator just means that if we have, let's say something like, whoa, what is that? Why did my pen do that? If I have something like square root of 3 over square root of 5. If I have a square root in the denominator, I want to rationalize that, so I want to get rid of the square root. I do not want square roots in the denominator. So in order to do that, we have to multiply by something, both top and bottom, that will get rid of a radical. So how do I get rid of a radical if I have the square root of 5? Well, think back to when we were just multiplying radicals, like square root of 5 times the square root of 5. When you're multiplying the same thing within the radical, you would get square root of 5 times 5 is 25. Square root of 25 is 5. And the relationship here is that if you're multiplying the same thing in a radical, you just get that same thing back. So square root of 7 times square root of 7 is 7. Square root of 10 times square root of 10 is 10. So square root of 5 times square root of 5 is 5. So that gets rid of the radical. So I'm going to multiply both top and bottom. And I guess this first example is a little bit similar to this, but that's okay. Multiply top and bottom by that radical, square root of 5. So on top, I get the square root, and they're both underneath the radical, so we'll get 15, not 13. Why did I write this 13? Square root of 3 times square root of 5 is 15. And then on the bottom, square root of 5 times square root of 5 is 5, as we just talked about. So there, I've rationalized the denominator. The radical is gone. So on number 1, I already almost did this problem. I just changed it to square root of 3. I wasn't even paying attention to my problems coming up. But 3 over the square root of 5. So I want to rationalize the denominator, meaning I want to get rid of the radical. So I'm just going to multiply by 5. Square root of 5. So on top, 3 root 5, that is not underneath the radical, so it's just going to be 3 square root of 5. Over, then square root of 5 times square root of 5 is 5. And some simplifying can happen in some certain situations, but in this situation it can't. 3 and 5 do not simplify. If this was like a 10, like 10 root 5 or something, then you could do 10 divided by 5. But that's just a 3, so we can't really do anything with that. Second one, 5 root 9 over square root of 4x. So first of all, before you just start rationalizing, look at the radicals and see if we can clean this up a little bit. And we can. We have the 5 square root of 9. Square root of 9 is 3. So this is 3, and then I'd have 5 times 3. So on the top I have 15, because square root of 9 is 3. 3 times 5 is 15. On the bottom, we can take the square root of 4. So that's 2. Square root of 4 is 2. And then I have this x underneath the radical. I can't do anything with that, so I'm going to have the square root of x still on the bottom, in the denominator. Now I'm rationalizing the denominator, so I want to get rid of that radical. The only thing I want to multiply by is to get rid of the radical. I don't want to multiply by 2 square root of x, because that's not rationalizing, or it's rationalizing the denominator, but it's causing us extra factors. Like, we can do that, but it would be extra work. So we don't want to multiply by 2 root x just because the 2 is on the bottom. We just want to multiply by whatever would get rid of the radical. So all we need is just to multiply by the square root of x, top and bottom. That's all we need to multiply by. So on top, we'll get 15 square root of x. 15 does not have a radical, so I'm not multiplying 15 and x. Then on bottom, square root of x times square root of x is x, times that 2, so we get 2x. And then 15 and 2 do not simplify, so I am done with that one. Check out number 3, the cube root of 1 over 3. Whenever we have a fraction inside a radical, we can separate the fraction into 2 separate radicals. So I could take the cube root of 1 over the cube root of 3. Cube root of 1 is 1, so I have 1 over the cube root of 3. Whenever we have cube roots or fourth roots or anything like that other than square roots, the thinking has to pick up a little bit. Like, we have to actually think a little bit here. And because I can't just multiply by the cube root of 3. If I just do the cube root of 3, like, if you just don't understand what we're trying to accomplish with multiplying by the square root, like why I'm multiplying square root of 5 times square root of 5, then this is going to seem a little bit weird, because I can't just multiply by this. Because if I do that, I get the cube root of 9. Is 9 a perfect cube? No. So that's not going to work. I can't multiply by just the cube root of 3. So think about what should you multiply by, because what we want is we want a number underneath this cube root to be a perfect cube. So then it's like, if I have the cube root of 8, for example, cube root of 8 is 2. No more radical. So that's my goal right now. And I have 3. So what do I have to multiply by? I have to multiply by the cube root of 9, because 9 times 3 is 27. The cube root of 27 is 3. So I'm going to multiply top and bottom by the cube root of 9. I know I'm pretty close to my camera here. Let me move this up. Cube root of 9 times 1 is the cube root of 9 over, and like I said, this is the cube root of 27 because 9 times 3 is 27. The cube root of 27 is just 3. So that becomes 3. So on bottom, I have 3. And then we cannot simplify cube root of 9 over 3, so we keep it as that. Number 4. I like to just take the fraction part and just separate it into two different radicals, see what happens here. So I'll have the square root of 2x over the square root of 3y. And this is a square root. Square roots are the easiest of the potential scenarios because you're just multiplying by whatever's inside that radical. So it's going to be times square root of 3y times square root of 3y. On the top, we get the square root. 3 times 2 is 6. And then x times y is just xy. So square root of xy over. And then on the bottom, square root of 3y times square root of 3y is just 3y. Whenever you're multiplying the same thing in the radical, you just get that, whatever that on the inside is. Number 5. A little bit tougher here. So number 5, we have the fourth root of y over the fourth root of 16x to the fifth. So like I said before on number 2, remember number 2, we cleaned it up a little bit. We tried to take the square root of 9, take the square root of 4, that kind of stuff. Do the same thing. So on top, I can't do anything with the fourth root of y, so I'm just going to leave that alone. On the bottom, though, we have the fourth root of 16. Fourth root of 16 is 2, right? Because 2 to the fourth is 16, so that's just 2. So no more radical for that one. And then I have the fourth root of x to the fifth. So that's going to be x to the 5 over 4. Simplifying that. 4 goes into 5 one time, so a single x will come out, leaving us with a single x left on the inside. So the fourth root of just x. Now I have to rationalize. So rationalizing this, I have to get rid of the radical. So I'm going to multiply by the fourth root, and I want this times this, whatever this is, to become x to the fourth. I want it to be x to the fourth, because like if I go back to this example right here, x to the fifth, let me bring this down a little bit. This is x to the fourth times x to the first. The fourth root of x to the fourth is just x, because it becomes x to the 4 over 4, which is just x to the first, leaving me with that single x. So that's what I want. That's the mindset that I want to be in. I want to get that exponent to be x to the fourth. So what do I have to multiply by? Well, if this is x to the first, I have to multiply by x to the third. Fourth root of x to the third, top and bottom. So let's do the fourth root of x to the third times y, because they're both underneath the same radical of fourth root. So x to the third times y, just x to the third times y. Then on the bottom, fourth root of x to the first times the fourth root of x to the third, that becomes the fourth root of x to the fourth, which is just x. So then I have x times x, which is x squared, so 2x squared. I'm going to erase this stuff right here. Next, rationalizing the denominator still, but we have a little bit of some different looks. Like if you look at number 6, 2 root 3 plus 5, I can't just multiply by a factor of root 3, because look what happens. If I do that, I'll have 2 root 3 times root 3, which will wipe out the radical. That will be gone. But I'd have to multiply the 5. So now I've just moved the radical to the 5. That's not rationalizing. I'm now just I'm just moving in a different location. So what we have to use is what's called the conjugate. So if I have like a plus b times a minus b, these are conjugates of one another, because it forms a squared minus b squared. So it's the first term being squared and the second term being squared. That's what we want to have in this scenario here. We want to think about conjugates. So on the bottom, if I have 2 root 3, I want to multiply by the conjugate of 2 root 3 plus 5. So that is going to be 2 square root of 3 minus 5. And whatever I do to the bottom, I do to the top. So I'm multiplying the top by 2 square root of 3 minus 5. This is the conjugate, because this was plus, so I have to multiply by the minus. And what ends up happening is the first term gets squared, so 2 root 3 squared, or 2 root 3 times 2 root 3, which is the same thing. It's just the radical is going to be gone. And then I just am left with this, 5 times negative 5. I don't have that radical anymore. So that's what we are trying to accomplish, and we're going to be good to go here. So let me just erase all my arrows here. So I'm doing 2 root 3 times 2 root 3, and then I'm doing 5 times negative 5, or just squaring the a and the b term. 2 root 3 times 2 root 3 is going to be, let me do the top first. I don't want to move this down a little bit. So I'm going to do 3 times 2 root 3, 3 times negative 5, and then I'll do the bottom. So 3 times 2 root 3 is 6 square root of 3. 3 times 2 is 6, minus 3 times 5 is 15. On the bottom, 2 root 3 times 2 root 3 is 4, 2 times 2, and then root 3 times root 3 is 3. Multiplying by the same thing underneath the radical, you get that term back. So it's just 3. Well, we have 4 times 3 here, which I'll do in a second. Oh, let me just do it now. So again, 2 times 2 was 4, times square root of 3 times the square root of 3 was 3. So I have 4 times 3, and that's going to be 12. I'm going to just rewrite this as 12. Then I have 5 times negative 5, which is going to be minus 25. So on top, 6 square root 3 minus 15 over 12 minus 25. Make sure you're not making mistakes there. That's going to be negative 13. So another step that you could take, but in this case it doesn't really do anything, is on the top I have 6 and 15. I could actually factor out a 3 from there, so then I'll be left with 3 times 2 square root of 3 minus 5 over 13, so we can make that fraction negative. Doesn't do anything though. If this was like a 12, you could simplify the 3 and the 12, but it's a 13, so it doesn't work out super nicely or anything like that, but you get the idea that you can factor and then simplify. Hopefully that happens in one of these problems here. So 7, we are rationalizing the denominator still. I want to multiply by the conjugate. So I have square root of 7 minus square root of 3. I want to multiply by the square root of 7 plus the square root of 3. So I'm going to multiply the top by the square root of 7 plus the square root of 3. Since we're multiplying a binomial times a binomial, we have to multiply it all out. So you have to do distributive property twice, or FOIL, whatever you've learned. So square root of 6 times the square root of 7, that is going to be square root of 42. Then we have square root of 6 times the square root of 3, which is going to be the square root of 18. And I know there's some simplifying we could do. We'll get there in a second. Plus 3 square root of 7 plus 3 square root of 3. Not super clean looking, but we'll see what happens on the bottom. I don't have to multiply it all out on the bottom because what we're doing is we're doing the conjugate. So it's just the square root of 7 times the square root of 7, which is 7, minus square root of 3 times the square root of 3, which is just 3. And the reason that's a little bit cleaner than the last one, because in the last one I had this 2 root 3 times 2 root 3, so that got a little bit more complicated. But we are in luck here where the bottom doesn't actually turn out to be a mess. The top is a little bit of a mess. Let's try to simplify these radicals. Square root of 42 does not simplify because square root of 42 is 21 times 2. 21 is 7 times 3 times 2. There's all prime numbers there, so nothing to do with that, surprisingly. You'd think 42 would have something, but it actually doesn't. Square root of 18, that is 9 times 2. Square root of 9 is 3, so we'll get 3 root 2 plus 3 root 7 plus 3 root 3 all over 7 minus 3 is 4. And I actually can't do anything else. There's no like terms, and this 3 right here, I know it's like looking pretty good, but there is no 3 here, so I can't factor out a 3. Wouldn't even simplify with anything, but there's nothing that I could even do there. I know I'm like right on the top of my camera here. Let me do number 8. I'm going to move this up a little bit. I'm going to do it number 8 up here. Kind of running out of room. So number 8, we have the 4 square root y divided by 3 minus square root of y. So we're going to multiply by the conjugate. So that's going to be 3 plus square root of y times, and then up here, 3 times square root of y, 3 plus square root of y. So 4 root y times 3, 4 square root of y times square root of y. And then on the bottom, we're going to multiply that out. So on the top, 4 root y times 3 is going to be 12 square root of y, plus 4 square root y times square root y is going to be 4y, because square root y times the square root of y is y. That's to be multiplied by the 4, so 4y. And that's it on top. On bottom, we just multiply it by the first term, 3 times 3, and when we do the second term, square root of y times square root of y. So 3 times 3 is 9 minus y. And same thing as I said before, you could factor out a 4 here. If you wanted to, you could take out 4. So 4, so that'd be 3 square root of y plus y over 9 minus y. It doesn't simplify at all or anything like that. And that 4 doesn't have anything to cancel out with. But either of these two answers would probably be okay. All right, let's move on to rationalizing numerators. So rationalizing numerators, same exact thing. If I have the square root of 7 over the square root of 2, same concept, just with the numerator. So I have to multiply by the square root of 7 on top and bottom. So that's going to become 7 over square root of 14. So it's the same exact process, same exact thought process, just rationalizing the numerator now. So number 9, square root of 5 over the square root of 15. I just have to multiply by the square root of 5. Square root of 5. So on top, I get 5 over square root of 15 times 5 is going to be, so you can do this a couple different ways. You could actually pull out a perfect square there if you want, but if you want to just multiply and then simplify. So I get the square root of 75, which is going to be 5 over, 75 is 25 times 3. Square root of 25 is 5, so 5 square root of 3. And then 5 over 5 simplified down to 1 over square root of 3. So that process again, 75 was 25 times 3. The square root of 25 was 5. So I pull a 5 out, and then I'm still left with that 3. Then 5 over 5 cancel out, so I just get 1 over root 3. Rationalizing the numerator. On the top, cube root of 9x squared over the cube root of 5y. So I want to first look to simplify if possible. Cube root of 9 is not a perfect cube, even though square root of 9 is. You know, you get in this habit of like 3's and stuff. Like, oh, I see the cube root, 9's got to do something. No, it doesn't. So I have to, there's nothing that simplifies. So now I have to rationalize. I have to multiply 9 by something to get me a perfect cube. I have to multiply x squared by something to get me a perfect cube. So I'm going to multiply by the cube root of 3, because 3 times 9 is 27. 27 is a perfect cube. X, because x to the second times x to the first is x to the third. 2 plus 1 is 3. What do I do to the top? I do to the bottom, cube root of 3x. So on top, we get cube root of 27, right? 9 times 3 is 27. X to the third, which is just 3x. Cube root of x to the third is x to the 3 over 3, which is x to the first. And on the bottom, I multiply by the cube root of 3x, and so we're going to have cube root of 15xy. And nothing can be simplified there. Alright, so rationalize the denominator. Rationalizing numerator, same process. You just got to get in this mindset of taking care of the numerator over taking care of the denominator, or vice versa, whatever you're trying to rationalize.